Fake or true? Have we looked at this one before in this class? No. I'm not sure it has anything to do with what we're talking about today, but they are falling in a fluid, a gas.
At 18,000 feet, the oxygen mask will come off. That will be from his cousin, Andy Barrington. Will be closest to him. There goes the oxygen mask. Now at 12,000 feet, you'll hear a beep in his helmet. That will tell him
You can see the part where everyone watches, I guess.
momentarily we'll see his jump team pull their chutes, and that means
Anyone here jumped out of a plane before?
he's all alone for the rest of the way.
Me neither. Don't plan on doing it either.
You'll get another beep in his helmet.
Must be quite a liberating experience. I'll let it take its course.
There goes the chutes. Luke is on his own. And the crowd on the ground looking up, they have a visual on him right now.
The Luke cam. Yeah.
He's in!
Not quite sure whether that's real or not, but you sure as hell wouldn't catch me doing it. So perhaps some of you might be reticent to try it as well. So yeah, I'm always curious as to whether that's real or not. It looks kind of real, but you never know these days.
It looks like something out of a science fiction film. A space-age paramedic jetting off to locate and treat a stricken hiker. But this jetpack could soon be the way medics in remote locations and difficult terrain reach their patients.
Yeah.
This simulated trial in the Lake District saw the response time cut from 25 minutes to 90 seconds.
Yeah.
The idea came as a result really of being kind of enthralled by the technology that Gravity were using and to see just how kind of maneuverable it was and wondering whether there would be enough space in
Interesting idea.
those kind of remote areas.
The kit consists of two
I guess interesting tag on the bottom. Biden-Trump debate. So I guess we know when this was last recorded.
in this trial. It says the future is
Not today.
The suit we're flying at the moment, in fact there's some behind me, that's the Mark II suit. The Mark III prototype is sitting just behind the camera on our development table there, and that starts in 10 seconds instead of 45 seconds for these ones. More like 60
Yeah, fine.
and
Right.
carry even more weight as well.
So,
This technology has been around for some time.
yeah.
In August last year, French inventor Franklin Zapata succeeded in crossing the channel in just 22 minutes.
English Channel.
His paraffin-powered device
22
had
miles.
speeds of up to 110 miles per
Yeah,
hour.
mentioned.
And when dealing with any casualty, speed is always a key factor. For some,
Yeah. So anyway, it's kind of what we're talking about today, what we left off with last time. And that is, we're talking about control volumes. So let's get rolling. Just recap. Anything else from last time? Any things we need to talk about? I think we're week 6, right? Halfway through week 7, you should have a topic uploaded onto Canvas for your presentation. So I've seen some groups chatting with each other. I think I told you already that when you email your group, it comes automatically to me. So don't say anything bad about. Well, you can do what you want in it, but you should know that it comes automatically to me for some reason. I've never quite worked out why that is. And so you should have met by the middle of last week, I think. And then by the middle of next week, week 7, you should have a topic. Matt will go through them, I think, just to make sure that not everyone's doing a golf ball, fluid dynamics of a golf ball or a thrown football or a bullet. They're doing something a bit more interesting and varied than that. So try and choose something that would be interesting for your colleagues to look at. And so that should be in place right now. Okay? Anything else? No. All right. So, well, as is customary for us, maybe we should just recap what we talked about last time. I will go through this. We talked about control volumes, and we haven't really done anything with them yet. I don't know whether I need to go, well, maybe just refresh our memories, because that will be something that we talk about. Not very good. We talked about static and non-deforming. And we talked about are you going to wake up for us? And we talked about moving and non-deforming. So that was our jet engine. And we talked about, I don't know how to draw it. I drew it as a balloon, right? And we talked about moving and deforming. So the idea is that they fall into these three categories, and I guess we'll talk about that at the end of today. We'll talk about Reynolds Transport Theorem, which allows us to accommodate those things. But it's no different when we're talking about conservation of mass than filling up a bucket with water, and you know the volume of the bucket, you know the rate at which you're putting water in, you divide the volume of the bucket by the rate, and you get the time it takes to fill it up. That's really what we're talking about, is conservation of mass. We talked last time about frames of reference, which of course is implicit in this, right? If it's moving, the frame of reference is changing. And I guess we made the point that if we look at plotting velocity versus space, if you think about me running across the front of the room, you could plot my velocity as I go across the room. It doesn't have to be a straight line. But if you wanted to get, at this point, my velocity, which we would call d, or acceleration, dv dt. So if there's an accelerometer attached to me, it would read how my velocity was changing with time. But if we want to get it for this particular point, we can also get it by merely getting the velocity and the rate of change of the velocity at that point. So this is dv dx, and we showed that this is equal to the velocity times dv dx. And it's also a half d dx v squared in bracket. And we showed that this, if I work out what the acceleration of this pen is as it falls down, same as a free jet, it's equal to gravity. That's all. So this is the best way I can explain it, is that we need to calculate what the acceleration is, because we want to use F equals m dv dt that's attached to the body that's moving across the front. Sometimes we don't know what that is because we're not attached to it, but we can see how, as you go in space, how acceleration would occur as velocity changes along a streamline, in this case going in the x direction. So this isn't a streamline, this is how velocity would change as you go horizontally. It's just charting it. And so that's physically what it means. It's just getting it from a different way. And that's what the material derivative, or substantial derivative as it's sometimes called, means, is that you can change it from attached to a person putting the sonde down the well bore to measure the temperature, and you can split it up as a function of how things change in space rather than how things change in time if you're attached to it. So that's it. So the other thing that we might attempt is to put that, I know there's a homework question that deals with this, and try and define the accelerations relative to streamlines. So this would be a streamline just in the x direction, and this is plotting how velocity changes as you go along that streamline in x. This is vx. But on a streamline, we might have a geometry which is slightly different, and we might want to calculate, I don't know why we'd want to calculate it, the accelerations in the x, the y, and the z directions. Whoops. Which is what this is. So this is a vector, and it's a function of the behavior along a streamline. And so the easiest way for me is to draw this out. And so imagine we have something like this. And this is a radius r. This is, I want this to be about 45 degrees, by the way, because I'm going to use that in a second. And this is the vector, which is the streamline. This is the vector which is normal to the streamline, which are these two things here. And I want to have a coordinate system which is x and y, and z would be coming out of the page at you, I guess. Don't need to worry about that. And we want at this point here the velocity to be the streamline velocity. I'll do it right here. Vs. So Vs is along a streamline, so it's a velocity, but it's really a speed, right? Because it does have direction, it has to be along the streamline, but it has a magnitude, and the direction is prescribed by the streamline. And so what we can do is we can look at these two components, and I'll remind you that these components is that if you write Newton's law along a streamline, it comes out to be mv dv ds, which is what this term is. And if you write it perpendicular to the streamline, it's equal to m vs squared over r. And this is just my sign for perpendicular, and that's this term. So this we know, right? We've called this the convective acceleration, which defines to move something laterally, its acceleration is defined in space. So the convective acceleration is just a substitute for the acceleration of the body. Likewise, the acceleration of the body, if it's going around a circle, if you're swinging something around your head, it's given by the radius of the string, the mass that's on the end of the string, and the speed that it's going around in that arc in terms of meters per second squared. So this is the centripetal, I guess, write it out. Centripetal acceleration. And this is convective. And so this is just saying that we can calculate what the accelerations are in these directions. So we've used this idea before. We've talked about the acceleration in the x direction, the acceleration in the y direction when we dealt with the statics. And so what we could do is we could take this point here and we could look at defining exactly what this magnitude is. So this is our S vector, and we just need to know what the components of that vector are. So, for instance, we want to know what this is. And in this particular case, S is going to be equal to 3 components. A component in X, a component in Y, and a component in Z. So if we make this unit 1, and then this by definition is square root 2, right? Just by Pythagoras. We want this vector to be a unit vector, so unit length. So if we divide this through by square root 2, and everything else by square root 2, then we have each of these components. So this vector S is going to be 1 over square root 2. This component is in the positive x direction, so it's going to be 1. This component is in the positive y direction, so it's going to be 1 times this length. And the z we don't care about because it's out of things. So this vector would be this. So in other words, if we multiply this vector through by this scalar value, so this is a velocity, 10 meters per second. This is a rate of change of velocity as it goes along a distance. So the units must be velocity divided by length, so it must be 1 over time, instead of meters per second divided by meters, 1 over seconds, in other words. And in the same way as that, we can define what this vector is here, and I guess this vector is going to equal this. Should probably do it larger. And this vector will equal this plus this. So again, if this is unit length here, this is unit length 1 over square root 2. This is equal to 1 over square root 2. And so if we look at the value of this, then what's it going to be? It's going to have 3 components. And those 3 components, the x component is going to be in the negative direction. It's again going to be 1 over square root 2. So this is going to be minus 1 because of this. And this is in the positive y direction. It's going to be plus 1 and 0. And again, this is multiplied by a scalar. This is a vector. The scalar is 10 meters per second squared divided by 4 meters the length. So it's the same as if I'm throwing something around my head, but this now is a streamline, and this is the velocity of the fluid that's going along it. It's changing velocity as it goes along that streamline. At a particular point, it will have a particular velocity, which is this and this. And if we know that information, we can calculate what the accelerations are in the x direction, y direction, and z direction, if we want them. We won't practically want them, but we could get them if we wanted to. And this is the expression that would give us that. And so we just have to get, so it's useful today for us to understand a little bit about how to calculate what vectors are, remind ourselves what vectors are, okay? Because in some of the things that we do, we've said already that when we're looking at conservation of mass, mass in versus mass out is a scalar quantity. It just has a value, it doesn't have any direction. But when you look at Newton's second law in conservation of momentum, it has an x component, a y component, and a z component, and so we typically have to worry a little bit about the velocities. Okay? So that's our preamble. You won't have to use this very often. You do in the homework, and we do need to know what vectors are. So you'd have 3 accelerations, one in the x, y, and z. The one in z would always be 0 because you'd be multiplying this scalar by 0 in each case and adding it to itself. All right, so now we want to talk about, if we've done this, we're going to talk about Reynolds transport theorem. Looks kind of scary, but it's not. I guess maybe while we're talking about vectors, we might talk about dot products. And And I talk about that because that term is here. And so what we want to do is to have a rational way of saying that if we have a flow V1 in the x direction, we want to calculate how much will go across this surface, which we'll call surface 1 perhaps. And it would have an area, A1, and the fluid going into it would have a density, bless you, 1. And so if we weren't being anal about it, we just do the calculation, and we just come up with the idea that the mass rate in, so we'll use this symbol, m dot. M is mass, dot is rate of change, so this is dm dt. Change in mass with time. Inside this control volume, so we'll call this control volume. CV. And we'll call this a control surface. CS. And so if you wanted to calculate how much mass is going into here, it would be the density, let's do it just with, it would be the velocity V1 multiplied by the cross-sectional area, A1. That would give us units of velocity times meters squared, so this would be what we often call Q, meters cubed per second. And if we pre-multiplied it by density, then this whole thing, I'm not dividing it by this would be meters per, this is in units of meters cubed per second. This is in kilograms per meter cubed. Multiply them together, you get kilograms per second, which is m dot. So this is the term. I'm not dividing it. I just can't draw squiggly brackets when I do it horizontally. And so that's one way that we can calculate that. And so what we might want to do is we want to set up a sign convention, and to do that, we'll set up a sign convention with a vector which defines a normal. Just like these were vectors that defined directions along a streamline and perpendicular to a streamline into the center of curvature, this is just a unit outward on the surface of this box. And our reason for doing that is that when we calculate the amount going into this box, we want to calculate the amount that's coming across this boundary perpendicular to the boundary. And we want to define whether it's going in or out, because it matters if our box is filling up from one side and emptying out for the other side. There should be a difference in sign convention. And so we use this so-called the dot product. And if we look at the dot product, then here the vector for velocity is equal to, what's it going to be? This is x, y, and z. It's going to be 3 components. It's going to be 1, 0, 0. 1 in the x direction, 0 in the y direction, 0 in the z direction, which is into the page, multiplied by v1. And we also can define this normal, which by definition is oriented as we show here. But by definition, it's always a unit length, just like our unit length was here. And this unit length here is going to be what? It's going to be -1, 0, 0. So it has a component here. So the dot product, if we take it, v dot n is just equal to 1, it's going to be v1 times 1, this term and this term, sorry, -1, plus 0 times 0, so this term and this term, Certainly you remember all this, and 0 times 0. And that is equal to minus V1. And so our sign convention when we look at this is that if flow is going into the system, it's negative. And if it's coming out of the system, let me do the same. Then this would be, so this is N1, and this is N1, this is V1. So this is N2, and this is V2. Then I'm running out of space, but let's do this over here. This is V2 is equal to what? It's going to be equal to exactly the same as before. It's equal to 1 in the x direction, 0 in the y, 0 in the z, multiplied by V2. This is a scalar. This is a vector, I guess. The normal to the boundary now for N2 is slightly different. Because it's oriented in this direction. This is going to be plus 1, 0, 0. Before it was minus 1, 0, 0. And if we take the dot product, V dot N, then it's equal to 1 times 1 times V2, I guess, plus 0 times 0 plus 0 times 0. And that is equal to V2 plus V2. And so all this dot product is a way for us to be able to put a tag on it which says that when it's flowing out of a volume, the mass rate is positive, and when it's flowing into a volume, it's negative. So it was convenient for us to talk about it now because we're dealing with vectors, right? So if you don't like dot products, really all it is it indexes it, so it does two things. It gets the component which is orthogonal to this boundary, which will be the maximum velocity and a unique velocity, and it multiplies it, indexes it, so it defines whether it's in or out. And it defines it because we always define an outward unit normal into our volume. So if you have a bucket, the outer unit normal is pointing in this direction on this side, and this direction on this side, this direction on the bottom, and this direction on the top, as it would be here. And you could do it for this. Actually, you could show this if you wanted to. You could show that the dot product of V1 dot N3, if this is N3, you could show that because these are orthogonal to each other, they won't have a component. So the dot product of the velocity V1 in this direction is going to be 0. Because if flowing in this direction, you're measuring the component vertically, and it has no component physically in that direction. That's what dot products do. That's all. So I don't want to belabor that point, but that's what we'll deal with. So what we're going to do, so we've saved you all this stuff. We've done this, blah, 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 blah. Yeah.
In this, what would Q, back when we were doing Theorem with DC, what would Q represent in that scenario besides work?
Q in terms of work.
No, I mean, because it's not work, what does Q represent in this case?
This is volumetric flow rate. Volumetric flow rate. Cubic meters per second. How much is flowing in a river or flowing into a bucket? Okay, right. So anyway, so we will deal with this thing called Reynolds transport theorem, which starts here. And this is the same expression that we looked at before. We talked about a pipe, stationary, control volume that's not moving. We talked about a jet engine, a moving one that's not deforming, and we talked about a balloon which is deforming. So these are the three different reference frames which we can choose to use. We won't do it today, but we can choose to use it. And this strange theorem after Osborne Reynolds, famous English fluid mechanician, says, if you want to write it out in terms, for us, this term here will always be 0. But this says that we can do a balance of things. We can look at a mass of fluid in our universe, which is the left-hand term, which doesn't change if we look at the mass within this room. And we can look at pouring it into a bucket. And if we pour it into a bucket, we can look at how quickly it goes in and how quickly it goes out. If it goes in at exactly the same rate as it comes out, then it won't accumulate. But any difference between the mass rate in and the mass rate out has to be the rate of accumulation. And so that's exactly what this expression says here. And so the idea is that we have, as we said before, we have a control surface, and I'll just label that as CS. And we have a control volume, which is enclosed by that control surface, CV. And you see those terms on this little integration. But this is just saying that if we flow a certain quantity into the system, and if we flow a certain quantity out of the system, the difference between these, so this is the addition between those, the exchange into or out of the system has to be an amount that accumulates. It's not saying anything more than that. And in this week and the next 2 weeks, so we're at week number 6 now, so we'll look at conservation of mass. Next week, we'll look at conservation of momentum, mass times velocity. And in week 8, we'll look at kinetic energy, so half mv squared. So we'll look at conservation of mass, momentum, and energy, as you'll see in the syllabus, for each of these 3 weeks. So 6, 7, and 8. And in each of these, we'll use this same theorem, which allows us to conserve mass or momentum or energy in our system. And so momentum is just F equals ma, a fancy way of saying that. We've already done that with Bernoulli, but it's the same as that. And energy is where we're conserving momentum, but where we allow losses in our system. So far, our system is inviscid, and so there's no viscosity, and so there's no losses. You go from point 1 to point 2, you have exactly the same energy as at those 2 points. You might have switched it between potential energy and kinetic energy, velocity, but they still, if you add up all the 3 terms in Bernoulli, they will be the same at those 2 points. And so when we do that for conservation of momentum, we're not losing energy, but if we look at dissipation of energy, which is the essence of fluid mechanics in some things, then we have to deal with that. So when we deal with conservation of mass, we have a so-called extensive quantity. It's written somewhere else. Yeah, okay. Yeah, I'll just write it. And so we have an extensive parameter, which we'll call B, and we'll have an intensive parameter. Doesn't matter what those terms are, which is B over mass, which is lowercase b. So it's all written out for you here. And so the only one we'll deal with today, which is plenty enough, is we'll deal with mass. And of course, if we look at the intensive property, mass divided by mass is equal to 1. So for us today, B is going to be equal to mass divided by mass, which is equal to 1. And so what I want to do is so for us, uppercase B is going to be mass, lowercase b is going to be mass over mass is equal to 1. So that allows us to put these terms into this equation. And this would be mass, but we're saying we don't care how that the mass in the room changes, even if some of it goes into our bucket and some of it comes out. So this term on the right-hand side is, for us, take it as 0. So we can write out this term. And we know that velocity times the dot product is just the amount going across a boundary. We've multiplied by a density and by an area. And so actually, if we scoot back to what we've done here, that is actually the mass rate of flow that's going in. A velocity times an area gives us volumetric flow rate. That's probably enough for us, but if density is not changing, it's perfectly good for us. If density is changing for some reason, we just need to pre-multiply it by that. So this term here is mass rate of flow. So what we could do is we could write this integral on the right-hand side as being, this is the sum of density times v dot n, let's write it as that for now, times area. Right? This is just a velocity across the boundary, indexed whether it's in or out, positive if it's out, negative if it's in. And this term we could write as d rho v bar dt. So if you don't like the look of this expression, we can rearrange it to look like a simpler expression. And this says that the mass flow rate in minus the mass flow rate out is the amount of accumulation. And the amount of accumulation is a rate of change of the product of density and volume, not velocity. I always cross my V's, uppercase V for volume. And so this is just the rate of accumulation. And that's all it is. So you probably don't need to know this Reynolds transport theorem. It's useful to know where these terms come from. And this is being done here. And so I'm going to write it out on I'm going to go back. So all you would need to know would be that conservation of mass which is what we're doing today. It turns out to be a rate of change with time of density times volume plus the sum of on all the faces of density times v dot n times area equals 0. And what we might want to do is we can split this term out. We can differentiate by parts, and if we do that, then it becomes a volume multiplied by a rate of change of density with time plus a density times a rate of change of volume with time plus sum of mass flow rates equals 0. And so that's the way to define it. And so if you want to think of this in terms of what we've done already, then if this is velocity 1 and area 1 and density 1, then the mass flow rate 1 is going to be equal to density 1, normal to the boundary velocity, which is going to be v1. It's in the opposite direction from the unit normal. So this is negative. So this is, if I can get a negative sign in there, and it's multiplied through by an area, which is the cross-sectional area A1. So it'll be, if the velocity is 10 meters a second, this would be minus 10 by definition. Likewise, if velocity v1 is coming out, or v2 is coming out, this is the unit normal, then m2 dot is going to be equal to the density coming out. It's probably the same, but it doesn't have to be. And of course, the area would be the area of this face, right? This whole face into the page. It would be plus V2 times A2. And so this would be positive. And so if you don't like dot products, then you just need to remember the sign convention. And I suppose the other thing is, we could note that so this term would be that dV, let me write it the same way as I had it here. So this is volume times rate of change of density with time, plus density times rate of change of volume with time is equal to, plus m1 dot plus m2 dot equals 0. That's what this expression says. So if the velocity going in and the velocity coming out are the same, then by definition these two will be equal to each other. And these terms, I guess they could be counter to each other, but these terms collectively would be 0, right? There's no accumulation. If the mass rate going in is greater than the mass rate coming out, then there'd be an accumulation. And that accumulation can occur in two ways. Either it can go in at constant density and the volume of our box can expand, which would be this term here. The volume of the box expanding with time, but it going in at constant density. So that would be pumping air into a tire that inflates. No, actually, that would be like flowing water into a bucket where the water level rises and the volume of the control volume, if you attach it to the top surface, changes. And the alternative would be pumping air into a tire, which probably does get a bit bigger, but largely the volume of the tire stays the same, but the air compresses to fit into it. And so that's what these terms are. So we talked about the sign convention for mass rate in is negative, mass rate out is positive. The other sign convention would be that if you look at the stuff going into this control volume with time, and if you look at the flowing it into a tire, then the density was changed with time. So this would be positive d rho dt. It's in that quadrant. This is positive, this is negative, just by calculus. And if we are flowing water into a bucket, and so in other words, our control volume, if you attach the control volume to this upper surface, and that control volume goes up with time, right? Then this could also be, I'll do it on a different diagram, but it'll be exactly the same as the diagram on the left. If volume changes with time, like this, then this is d uppercase V dt. So if you're net accumulating mass because the density is increasing as you're pumping it into your tire, that's a positive change here, this one, and likewise for this volume increasing. So that's it. Got time for a couple of very quick questions. Everyone fine with that? So the equation that you'll probably be using will be this. Not Reynolds Transport Theorem, but you see where it comes from. And actually, we can use Reynolds Transport Theorem to also look at conservation of momentum, but we won't do that today. Okay. So, yeah.
Would normal force on either side be represented as m1 equals m2, or are they equal in this case, or would they still would
Not talking about forces at all.
would,
We'll talk about, believe me, we'll talk about forces next week, and it gets more, forces are more complicated, right? Because we're talking about filling things up. So it's either positive in, negative in, or positive out. So it's a scalar. When we deal with forces, we have to look also not only as its magnitude, but also its direction. And so it's more complicated. So forces aren't involved in this yet.
then to, I guess, to rephrase, is for this specific sense for the control volume, would the n's be represented as n1 and n2 as like before, or would they be equal?
They're of length 1 in each case, and they're of different directions. So n1 would be -1, because it's pointing in the, well, I'm not sure how I appear relative to the screen. This will be the same, this one would be -1, 0, 0, just as before. And n2 would be equal to positive. This is the x direction to the right. This is +1, 0, 0. So the other property that this unit normal has is that if you sum up the sum of these squared, it equals 1. So -1 squared plus 0 squared plus 0 squared, it is always equal to 1, which is Pythagoras' theorem saying that the length of this unit, irrespective of how it's oriented, is always going to be equal to 1. It's x squared plus y squared plus z squared. Okay. I do want to go through 2 examples, so it's just not theory we've talked about. So this is just the idea. So, blah, blah. So this is the same idea as before. These are the expressions we're dealing with. And let's just talk about filling a volume up with a fluid going in. We've talked about the equation we end up with, which is this. And so what we could do is we could look at two examples. One is the exact examples that we talked about. One is pumping up a tire. So we have a tire, it's closed off. We're going to pump air into it at velocity v1 and rho 0 as it goes in. The volume of the control volume, so VCV is equal to this. And so we can write our expression in terms of rates, mass rate in, the sum of the mass rates in is equal to the rate of change of volume of the control volume with time times the density plus the volume of the control volume multiplied by the rate of change of density. So what do we have in here? The control volume is not changing size. So by definition, dV dt is 0, hence this term here. We know that this term here is going to be equal to area 1 times density 0 times velocity 1. We know that we're going into it, and so this should be negative, I guess, right? So area 1, rho 1, v1 is this. Rho 1, v1, area 1. It's negative. There is no fluid coming out of here, so this is v2 equals 0, so there's no term. 0 times the unit normal is 0. And so there must be something to balance the amount that's going in, and it has to be the accumulation. The volume isn't changing, we've already set that 0, but the density has to be changing. It goes in at some density, it gets larger because you're squeezing it in there. And so the constant volume multiplied by the rate of change of density gives you this, and so this is our conservation expression. That's all we need. And so what we might want to do is figure out what the density is when we've finished pumping into the system. So we can take this, we can multiply both sides by dt. We can integrate both sides from the initial density to the final density, from the initial time to the final time. The integral of this is just t. And if we evaluate it between the limits of 0 and t, it's t minus 0, right? So that's this term here. If we integrate this, this is just dp evaluated between these limits. The final density is this one. The initial density is this one. Multiplied by volume, we have this. And so we have everything we need to know. We know the density it goes in with in the beginning. We know the volume of the tire. We know the initial density. We know the velocity at which it's going in. And we know the area over which it's going. So this term here, with what we'd be calling Q, this would be just our volumetric flow rate, meters cubed per second. And we can solve for the final density. That's it. So the other problem to solve would be by doing this. And we'll do this more next time. And that is now that instead of filling a tire, we're going to fill a bucket. We're going to fill it from the bottom. And we're going to attach our control volume, even though I'm doing it in red. Our control volume is going to be this. And we're going to allow the control volume to increase in volume, because we're going to attach it to the surface of the water. We're putting water into the system. This is going to be the same as before. This is going to be rho 0 V1 times A1. This is kilograms per second. There's no fluid escaping our control volume because we're anchoring the top of the control volume to the free surface, which is rising. And so we can look at these two components. The density of the water that's going into it isn't changing very much because it's still atmospheric pressure. So we know that the change in density as we pump it in isn't changing. But the volume of our control volume is changing. And so we can write the expression as this. This is going in, so this term here has to be a negative. And the other term which we have is that the volume's changing with time, and we can write that out. So it's equal to 0, so we can equate each of these two to each other just by this. We can multiply both, we can divide both sides by rho 0. We can multiply both sides by dt. And so we have this. And then if we write out the volume as equal to this area here, call it A2, then the volume is equal to A2, the bottom planned area of the bucket, times the height. The height is growing, right, with time. And so if we write, this is just the volume, we can write it as a function of the height. We can do the integrations. If the initial height is 0, then the integration of this just becomes the height of the top. And so we know the rate at which we're pouring it in. We know the pipe diameter which is pouring it in. We know the cross-sectional area of the bucket. And we know that we want to know how high the top is after 10 seconds. And this is the only parameter we can solve for. That's it. Solve. So not so simple, but there are some simple rules to remember. And the simple rules are, I guess we have it on the page. You just have to remember the sign convention that we talked about. And that is that if you're flowing stuff into the system, it's negative. If you're flowing stuff out of the system, it's positive. If you're net increasing density with time or volume with time, those are both positive. And if you use that sign convention, everything should be fantastic. Okay. That's it. Okay, that's it.